Hello, I'm Chris Walker, and for this project I will be considering a hypothetical neural network which uses carbon nanotubes for synaptic neural connections. The rationale for considering neural networks is their incredible computational power. Because of their somewhat amorphous parallel construction, they can do massive parallel computations on different concepts at the same time. This also leads to a fault-tolerant and adaptable nature, as seen in humans who have lost part of their brain and yet are still able to function in a semi-normal fashion. Now contrast this to the current state-of-the-art in silicon computers. Silicon computers are based upon the inherently serial, theoretical model of the Turing machine, which consists of a tape, a head, and a table. The tape is an infinitely long instruction set of symbols. The head reads one of these symbols at a time and refers to the table for which action to take based upon which symbol it reads. This serial construction works perfectly fine in theory as long as the head can move infinitely fast. But when put into practice, in something like the von Neumann architecture, which most computers use today, there's a division between CPU and memory, and this causes a communication bottleneck when one is trying to achieve more rapid performance. In order to increase the computational power of computers, it may be necessary to move to a more parallel architecture. Unfortunately, current silicon computers are also incredibly bad at fault tolerance, and they are incredibly bad at adapting to new complex situations. For prior work, the state-of-the-art is definitely biological. The person reading or listening to this presentation. The average human being has at least 10 billion neurons and over 0.1 quadrillion synapses. Now, in comparison with artificial work to this point, that is mind-boggling. IBM created the Zero Instruction Set 36 and 78 digital computers, which, rather than relying on programming and other higher-level software, use direct hardware pattern matching with inputs of up to 64 bits. These only have 36 to 78 neurons per chip, but they can be used in parallel to increase their computational size. On a similar note, Intel created ETAN, the electrically trainable artificial neural network. This has 10,240 synapses with an area of about 2,000 micrometers per synapse. Stanford is currently working on the Brains in Silicon project, which is a novel merger of analog and digital neural network emulators. On the low level, analog circuits are used to emulate the behavior of each individual neuron, and yet digital connections are used to set up synapses between the neurons. The biological neuron itself is incredibly complex, and therefore only a small level of detail will be considered in this presentation. Each neuron has a cell body, or soma, an axon, and dendrites. Dendrites receive signals in the form of neurotransmitters from other neural cells. These signals are then transmitted through the soma to the axon, where they're sent out as an electrochemical potential to the end of the synapses on the neuron. Most neurons have an essentially binary operation, where they're not activated as long as the stimulation from other cells is below a certain point. But as soon as the other cells stimulate them to a certain extent, they will fire and send a signal out from their axon. This in turn can stimulate other cells, causing pulses of activity throughout neural networks. The concept for this project is to create an inorganic, low-cost, scalable emulation of this simplistic behavior of individual and connected neurons. For an energy source, we obviously do not have access to a cellular metabolism, nor do we want to constrain ourselves to operating within a current technology silicon grid. Therefore, instead, we will use illuminated microscale photodiodes as an analog to cellular metabolism. When hit with light, these photodiodes will build up a voltage potential, which can be used in order to signal between adjacent neurons made out of these photodiodes. This is an electric signal, which is a close analog to biological neurons, which also use an electric signal in terms of an action potential created by diffusing cellular chemical species. In the long term, neurons also have the property that they can learn or retain information by path weighting, changing the weight between connections of neurons. They do this by varying their synaptic connections. Most analogs, or most emulations of biological neural systems, use binary information amplifiers or some other system to represent the long-term learning. In this system, we will actually consider the physical absorption of an amphiphilic surfactant on the surface of the connecting nanotubes. The way it works is like this. When a long-term signal is memorized by the connection between two adjacent neurons, a coating of this amphiphilic surfactant will build up on the connecting nanotubes. This surfactant is also an electrical insulator, which will increase the amount of signal which can get transferred from one neuron to another, thus strengthening the connection.